Hello students. In last two lecture we have discussed about the Lagrange equation, Hamilton variation principle and derivation of Lagrange equation from the Newton's equation. Today we will discuss about some numericals, or we can say derivation of Lagrange equation in the physical problems. So first numerical, let us discuss about the setup Lagrangian equation of motion for the one-dimensional harmonic oscillator. Let us suppose an harmonic oscillator that is vibrating about the x-axis. Then let the force for one-dimensional harmonic oscillator is represented by this equation: F is equal to minus kx, where k is the spring constant. Also, the force can be written as minus gradient of potential, that is equal to F is equal to minus dV by dx. So dV from here will be equal to the minus F dx, and F is equal to minus kx. Then putting the value of F, we will get dV is equal to kx dx. Then finding the potential, integrate this equation, we will get V is equal to kx dx का integral, and that is equal to 1 by 2 kx square plus c, where c is the integration constant and can be determined choosing the horizontal plane passing through the position of equilibrium as the reference level. At reference level, as we know that the potential energy will be equal to 0 at x is equal to 0. Then putting at x is equal to 0, v is equal to 0, we will get c is equal to 0. Then the potential becomes 1 by 2 kx square, that is the potential energy. Similarly, kinetic energy of the particle of the mass m at a given distance x is given by 1 by 2 m x dot square, where x dot square is the square of the velocity, as x dot represent the first derivative with respect to time of the position, and similarly gives the velocity. Then Lagrangian for the oscillator is given by L. L is a Lagrangian function that is equals to the t minus v, and t is kinetic energy, v is the potential energy. Then this will be equals to the kinetic energy 1 by 2 mx dot square minus 1 by 2 kx square, that is the potential energy. Then as we know, the equation, Lagrangian equation is given by curl L by d by dt of curl L by curl x dot minus curl L by curl is given by, let curl d by dt of curl L by curl q dot minus curl L by curl q, let q k, if there are the k generalized coordinates, is equal to 0. Then let us find the value of curl L by curl q dot and curl L by curl q. As L is given by this equation, then finding the value of curl L by curl x and also curl L by curl x dot. Curl L by curl x will be equals to the simply, as first term in this equation is the function of x dot, so derivative with respect to x will be equals to 0. Then there will the only derivative of the second term minus 1 by 2 kx square, derivative करें तो इसका आ जाएगा 2x multiply by the 1 by 2k, that is equal to minus kx. Similarly, we can find the value of curl L by curl x dot, that gives 1 by 2 mx dot square minus 1 by 2 kx square. Then second term, as here second term is not the function of the x dot, so derivative of this with respect to x dot will be equals to 0. Then we will get only the derivative of this first term that is equal to 1 by 2 mx dot square, and derivative of this will be equals to the 1 by 2 m 2x dot, and then will be equals to the mx dot. Then taking the derivative with respect to the time, it gives mx double dot. Then putting these equation in the Lagrange equation that is given by this for the motion of the oscillator, then putting the value of d by dt curl x by curl L by curl x dot will be equal to the mx double dot, and minus curl L by curl x is equal to the minus kx, which will be equals to 0, and from here we get mx double dot plus kx is equal to 0. That is the required equation. It is an equation of simple harmonic motion and can be put in the form of the general equation that is given by the x double dot plus omega square x is equal to 0, where omega is the angular frequency that is equal to the 2 pi by t. Then comparing these, let this the equation 1 and let this be the equation 2. Then comparing these two equations, we can find out the time period. As comparing these, omega square will be equal to the k by m, and then omega is equal to the 2 pi then equating omega is equal to, that is the angular frequency, 2 pi by t, and then finding the value of t, we will get t is equal to 2 pi m by k square root. That is the time period t of the oscillation. That was all about the harmonic oscillator. Similarly, next is the example of the simple pendulum. Then let us a pendulum having the length of string is given by the L, where let A is the point of equilibrium. Let at any instant the pendulum is at a point B that makes an angle theta with the origin O with the equilibrium position. And then let draw a perpendicular BC on the OA. Let M be the mass with the origin O as point of suspension, and equilibrium vertical length is equal to L. That is the length of string. If at an instant t the string OB of the pendulum makes an angle theta with its equilibrium position OA, then kinetic energy is equal to half mv square, that is equal to V is equal to R omega, as we know that V is equal to R omega, and here R is equal to L, and omega is equal to the first time derivative of the angular displacement and angular displacement here is the theta. Then this L theta dot, where theta dot represent the angular velocity, then linear velocity will be equal to the L theta dot. So V square will be equal to the L square theta dot square. This is the kinetic energy of the pendulum. And as transversing a distance from A to B, the boom of the pendulum has covered a distance CA. That means the potential energy is increased by this length CA. Then V, that is the potential energy, will be equal to the mg into CA. And CA, we can find out the value of CA, that will be equal to the OA minus OC. And OA is equal to L, and value of OC from the triangle OCB, that is right angle at the C, will be equal to the L cos theta. and then potential energy will be equal to the mgl 1 minus cos of theta. Where the reference level, that is the point of zero potential energy, is taken at a distance L below the point O. As this line, this line here is taken as the reference level for the zero potential, then the L, the value of Lagrange function L, will be equals to the T minus V, putting the value of T and V. And then similarly, we know that the Lagrangian equation in generalized coordinate theta will be equals to this curl d by dt of curl L by curl theta dot minus curl L by curl theta will be equals to 0. So we will find out here curl L by curl theta dot. L is given by this equation. Then curl L by curl theta dot will be equals to the derivative of this first term, as second term is independent of the theta dot. So derivative of this first term in the equation 1 will be equal to the 1 by 2 ml square to theta dot. Then 2 से 2 cancel. Curl L by curl theta dot will be equal to the ml square theta dot. Similarly, curl L by curl theta will be equal to the minus mgl cos का डेरिवेटिव करें तो हमारे पास आ जाएगा माइनस साइन, then minus minus plus, then minus mgl sin theta. Then putting these values in the equation second, we will get dy dt ml square theta dot plus mgl sin of theta, that is equal to the ml square theta double dot, that is the double derivative of theta with respect to the time, and gives the oscillation. This represents the oscillation, that is the double derivative with respect to theta, angular oscillation. This is equal to the mgl sin theta. Then we can cancel m as well as L square, then this will be equal to the theta dot g by L sin of theta. And as theta is very small, so sin theta can be taken as equals to the theta, then this will be equal to the theta double dot g by L theta is equals to 0. Similarly, as we have compared in the last numericals with the general equation theta dot square plus omega square theta is equals to 0. So similarly, we can find out here the time period of the pendulum. So omega square will be equal to the g by L. So from here t will be equal to the 2 pi square root of L by g. There will be the time period of the this one dimensional this simple pendulum. Similarly, next that is very important also example is the Atwood machine. Atwood machine की अगर हम बात करें तो वहाँ पे oscillation निकालने के न्यूमेरिकल काफ़ी बार आ जाता है कि फाइंड आउट द oscillation for the Atwood machine. Here, this is the Atwood machine where the two masses, first M1 and second M2, are suspended over this frictionless pulley, and let radius of pulley is given equals to the A. Let a mass M1 is at a distance x1 from the let this reference line that passing through the origin of the pulley. Similarly, M2 is at a distance x2 from the same reference line. As this is taken as a reference line and mass M1 and M2 are just below this reference line, so potential energy here we will take negative. That just is so that the mass or the position of the masses are below the reference line. Initially, let us calculate the values of x and y in the x and y. Let x1 in the x2, and then we will replace x2 with the x1, and we will get the equations in a single coordinate. So here, as we know that x1 plus x2 plus half circumference of this frictionless pulley. Circumference is given by the 2 pi r, then half will be equal to the pi r, and r is here small a. Then this x1 plus x2 will be equals to the x1 plus x2 plus pi a will be equal to the L, that is the radius. Then taking the first derivative x1 dot plus x2 dot plus 0, as pi a is not the function of time. x1, x2 are varying with the time. Pi a is constant, L is also constant, so derivative will be equals to 0. It means x1 dot will be equal to the x2 dot. Then taking the second derivative, we will get x1 double dot will be equal to the x2 double dot. And here it comes the x2 double dot, that is the second derivative, will be equal to the minus x1 double dot. Kinetic energy of the mass m1 will be equal to the 1 by 2 mx1 dot square, that will be equals to the 1 by 2 m1 x1 dot square. And similarly, kinetic energy of the mass m2 will be equal to the 1 by 2 m2 x2 dot square. Then replacing x2 dot with the x1, that is equal to x2 dot was equal to the minus x1 dot, and then this will be equal to the same 1 by 2 m2 x1 dot square, as x1 dot is equal to the minus x2 dot, but taking the square, x1 dot square will be equal to the x2 dot square. So total kinetic energy will be equal to the 1 by 2 m1 plus m2 x1 dot square. That is simply the total kinetic energy of the system, 1 by 2 m1 plus m2 x1 dot square. Then finding the potential energy. Considering a horizontal plane that is passing through the A, this, let us consider this plane, sorry, I am not, this plane that is passing through the A as the reference level. And the m1 and m2 are the masses which are below this reference level. So we can take this negative, the potential energy, as the negative. That just show that the masses are at the below at reference level. So potential energy of the mass m1 will be equal to the minus m1 g x1, and potential energy of the mass m2 will be equal to the minus m2 g x2. Then total potential energy will be the sum of these m1 minus m1 g x1 minus m2 g x2. Then replacing x2 with the x1, we will get x2 will be equal to the L minus pi a minus x1 from the equation. First, let use the equation, this equation let a या first जो भी equation मान ले हम इसको यहाँ से. Then solving this, taking m1 minus m2 minus m1 and minus m2 into g x1 and plus हमारे पास आएगा माइनस जी एम टू एल माइनस पाई ए. इसको सारे को हम कांस्टेंट मान लें, माइनस जी एम टू इंटू एल माइनस पाई ए. इसको हम वी नोट के इक्वल मान लें, दैट इज कांस्टेंट, एज इट इज कांस्टेंट. सो टोटल पोटेंशियल एनर्जी विल बी इक्वल्स टू द माइनस एम वन माइनस इंटू एम वन माइनस एम टू जी एक्स वन प्लस वी नोट. सो टेकिंग द t minus v, as L is equal to t minus v, so putting the value of t and v, we will get L is equal to this. Then finding the curl L by curl x1 dot and curl L by curl x, you find out these two derivative, and then put these in the Lagrange equation that is given by this equation. Then curl L by curl x1 will be equal to the m1 plus m2 into x1 dot, and curl L by curl x1 will be equal to the m1 minus m2 into g. Then putting these in this equation, we will simply get that d by dt into curl L by curl x dot was equal to the m1 plus m2 into x1 dot, and minus curl L by curl x1, that is equal to the m1 minus m2 into g is equals to 0. And then taking the derivative of this here, x1 dot d by dt of x1 dot will be equal to the x1 double dot, and we will find the value of x1 double dot, that is the acceleration. So taking this term in this side, m1 minus m2 into g upon m1 plus m2. So finally we will get the value of acceleration, that is given by m1 minus m2 upon m1 plus m2 into g, that is the acceleration of the Atwood machine. Initially we have given this acceleration and we have found it by the Lagrange equation, that is the acceleration of the Atwood machine. Another example for the Lagrange equation is obtain the Lagrange equation for a single particle moving freely in the space in Cartesian coordinate as well as in polar coordinate, that we will discuss in the next lecture. Okay, thank you.